Yeah, thanks for the introduction, and it's great to see so many of you here in the office. It's great so many people are interested in coming to hear about Stripe. I'm Mark, I'm an engineer at Stripe, and I work on developer productivity, specifically on coding agents at Stripe. So loosely everything related to shipping code with AI tools at Stripe across the whole software development lifecycle. This talk is going to be fairly fast-paced. It's going to be an introduction to how, generally, how many Stripes are using AI to write code and the adoption we have here at Stripe, and then specifically going to talk about minions, which are our one-shot coding agents. If that doesn't sound familiar yet, don't worry. I'll introduce it from the beginning. Just to sort of frame the problem at Stripe, there's about 5 million businesses running on Stripe all across the world. In last year, cumulatively, those businesses processed close to $2 trillion in transaction volume. So there's very few, that's roughly like 1.6% of the world's GDP. So there's very few countries in the world, and especially in the European Union, there's only a low single-digit number of countries that have an economy greater than that of the size of the economy running on Stripe. So the opportunity for us to leverage AI to benefit such a wide economy is huge, but also we still have huge security, reliability, and quality obligations to our users. So sort of going to touch a bit today on how we balance the two of them in tandem and leverage AI effectively across our organization to boost productivity, but while still keeping our customers' needs first. So today, with that in mind, 91% of Stripe engineers are writing code every day with AI tools. 100% of Stripes are leveraging AI somewhere across the software lifecycle. And in the last year, we've seen almost a 500% increase in AI-generated pull requests. So massive growth combined with a pretty high-stakes problem space. So today we can talk a bit about how we're thinking about those problems. So at Stripe, we have lots of different types of coding agents. We have the standard harnesses most people have and pretty much accessible to anyone, that being Claude Code, Cursor, or OpenAI's Codex. So yeah, we want to make sure our engineers have access to all the latest models. Stripe engineers have unlimited access to these models, so there's no cap on how many tokens you can spend or how much money you can burn. So Stripe's a really great place to learn more about using these harnesses. But most of what I'll touch on today will be minions, which are homegrown coding agents. So this is a coding agent platform we've built ourselves for more autonomous and hands-off development. So the first three harnesses I mentioned, the developer harnesses, they're more suited to a co-pilot style interaction where you have a developer working in tandem with a CLI agent or a desktop app in Cursor's case. But minions are specifically for one-shot tasks. So that may be an unfamiliar term, so I can explain that a little bit. I'm just going to give you a demo straight away of someone using a one-shot agent to solve a problem. Our one-shot agents are typically launched from Slack, but they can also be launched autonomously to resolve Jira tickets or things like that. I'll touch on that in a minute. But here's me talking on Slack with an agent. And we have close to 700 MCP tools at Stripe that do everything from you can get the temperature of an air conditioning sensor in the office, or you can ask it about a branch. In this instance, I'm asking a tool to get the diff between a branch and master. So what does some code change an engineer made look like compared to master? And this is one of hundreds of MCP tools. Not super relevant, but this is just an example of some trivial bug I found while working on something else. So we can see there's some kind of malformed diff being produced by this tool. So I tagged an agent and just want to investigate what the problem was. And you can see here that the agent identifies the problem pretty quickly. It's actually very simple. Just for a purpose of example, it's just a 3-character mistake, and it actually proposed a fix. So at this point, these are the sort of problems we think are very one-shottable, or we can just hand off to a one-shot agent to take over from now. So the next step for this, if we just want an agent to take over and solve this problem for us, given we're pretty confident what the solution is literally just to say, @devbox, which is analogous to @minion, fix this issue. This is the most simple form of prompt. We could make it much more complicated or contain more context, but this is just in its most simple form. So a developer can make this call to Slack, or make this send the Slack message, and you see this emoji has arrived of the little minion saying 1 second. And then sometime later, the engineer can expect to see a response like this. Just say, your agent run completed, time to see how it did, and there's a button there the engineer can hit to see the changes. So first of all, like, why do we think it's valuable to make changes like this? So when we have like these AI agents, it's great to use them as like a co-pilot to boost your productivity as an engineer. Like, you can make plans much quicker and iterate on plans, but there's also a lot of time we can save where engineers are making very trivial code changes, or not even just small in size, but something where the engineer has a very good idea of what the change will look like before they go to implementation. So we don't think it's valuable for our engineers, now that we have these agents, to spend time creating branches, creating pull requests, and with their hands on the keyboard. And even if it's create a branch, start a coding agent, and start talking to this coding agent about, oh, okay, this is how we're going to implement it, do this, turning their attention somewhere else, coming back to the coding agent, their attention is being like diverted for a very small change. So we want to empower engineers to just kick off these agents and just go from one prompt to a PR in like one go with no engineer attention required in the middle. And one other thing we've learned is if your session was only a few prompts, it could probably have been one-shotted. So if you are using Claude Code and you have these very long sessions, you might actually go back and see that the input from you, the engineer, is only like 3-4 lines of input. In that case, if you had the conversation up front with another agent and then kicked off the coding implementation, you probably didn't need to be like in the loop the whole time. You probably could have had the conversation up front and then kicked off the coding agent afterwards. So that's like kind of why we use one-shot agents. But let's talk a bit about how that actually happens. So we sent this message on Slack. How do we go from that to a pull request? Obviously, like, a lot has to happen in the middle there. So at Stripe, we're sort of fortunate that upfront, long before coding agents were a thing, we already invested in remote development. So Stripes don't write code on their laptop. They write code on remote developer environments. These are not like one-to-one engineer to machine. So Stripe engineers can have as many of these as they want. Typically, we use like one per branch or per task, so you can parallelize between them. They're ready in less than 10 seconds. You could talk a lot about why we need these. Our monorepo is roughly 275 million lines of code, so there's a lot of like scale challenges that come with that. Running like bundle install in our Ruby code base takes a very long time, so we want to maintain this pool of dev boxes that are, our remote machines are called dev boxes, this pool of dev boxes that are always ready to go and can just be assigned to agents really quickly, or to developers really quickly. But what we've learned now is they're also really great homes for agents. So when one of these minions gets kicked off, the first thing we do is give it some compute that has our code base on it, has like a fresh clone of master, everything running and like ready to for the agent to start working on. And yeah, here's an agent in its new environment. So we have this agent now with a goal given to us by a developer, and we have a piece of compute to run the agent on. So our next question is, like, how do we actually implement the change? How do we get to the goal from where we started at? And the first thing we do is we start the minion up on this dev box. So on this new piece of compute we've gone from a prompt, gotten the compute, and we're going to start the minion loop now. So the minion loop is how we think about like going from the goal to the pull request. Like, how do we achieve that goal? So the first thing we do is we take the prompt that the user gave us and the Slack thread that the messages were gathered from. If there was like tickets mentioned in the Slack thread, if there was pull request mentioned, we kind of gather all that information and hand it to this analyze prompt agent. At that point, we're ready to figure out like what this code change is going to look like. So we figure out what part of our monorepo, so what language we're going to be writing roughly for the majority of the change, what part of the code base we're going to be writing in, and then that's when we're ready to actually start the loop. So the first part of the process is taking the prompt and the information associated with the prompt and handing that to a coding agent. So much like the coding agent like Claude Code or Cursor you might have used before, we first sort of do this like autonomous step to take the human away to analyze like what change are we making, and then we start the actual implementation. So what does that look like? So the implementation loop looks something like this, where we start at this white arrow in the top corner, and we take the Slack thread, all the conversational context that I mentioned, and we put that into the, we put all that into the agent's context, and we say, okay, what is the next step? So this is all happening autonomously. The agent says, okay, I'm going to plan the next step, and then it goes and makes the the actual code change, whether that's running like generated files or editing files itself, running bash commands, etc. Does all that, and then it validates its change. Much like you would if you were just using a coding agent yourself, but we're running this in a loop. So every time the agent makes a change, we use an LLM judge, so we fire up another LLM, and we say, okay, this was the prompt we gave to an agent, this is the diff or the output it produced. Given those two things, do you think we've accomplished the task? Have we completed what we're trying to do? Have we achieved the goal of the engineer? If yes, great, we can just go and create the pull request and go back to the engineer and say, super, we have something ready for you. Go review this. If not, we then get another agent to diagnose what happened. So why have we not achieved the goal? Is it because we just haven't finished writing the change? Is it because some test was failing? What actually happened? So we take that information then and put it back into the loop. So we start running this continuous loop of, this was the user's original goal, this is what we've done so far, what do we need to do to achieve the change? We run this continuously in a loop, like up to 10 times, I think. And at that point, we just fail back to the user. That happens in less than 1% of cases. So we usually always create a pull request. The question is, will the pull request be exactly what the engineer wants? Not always the case. But we merge without changes about 65% of minion pull requests. So one shot, 65% of the time. An engineer doesn't touch any of the code. It just goes straight into production after review. The other 45% of the time, or 35% of the time, sorry, the engineer typically takes over and makes some kind of change. At that point, they can open up what the minion did in a web surface. So you can see here, this is like the end of a minion run. It looks like here it was diagnosing some test failures, and then later on you can see it open a pull request. At this point, the engineer can open the pull request and approve it, or get someone else to review it too and approve it. Or they can hit in the top right corner here, you can see we have buttons to open, for example, like VS Code, an editor to take over what the minion was just working on. The dev box is already ready for the engineer because the minion was using it. And then similarly, even in the web surface, they can just hit console button and open a terminal here, and open maybe like a terminal editor or whatever they want to use. So yeah, that's the story of how we go from this little coding agent to something slightly more powerful that can make end-to-end changes in Stripe's code base. We're merging 3,000 pull requests a week at Stripe with minions alone. So lots of non-zero amount of Stripe's code base changes come from minions. So briefly, I can give you a few insights to take away from this, sort of what we learned along the road of building this. So prompts are great. So we have lots of prompts, as you can imagine, and we have lots of moving pieces in minions. The LLM judge to decide if it's, we've completed the task, the actual coding agent loop, then the diagnostic agent, which figures out why did we not complete the task. Lots of prompts there, and they're great. But if you're writing prompts for that sort of thing, say in the coding agent loop, you always want to run lints before you make a commit and decide if the task is complete, right? So if you're writing a prompt that looks something like, do not commit before you've run linters, or please run tests before opening a pull request, and all capital letters maybe, you're screaming at your agents trying to get them to do something. We found that deterministic instructions are much better for this. So instead of writing these giant prompt files that say please do this, don't, take this step before you've done something else, actually pulling this out into some deterministic code in a loop, it increases the success rate of these things exponentially. So yeah, deterministic instructions for these loops are pretty much critical. Our other big takeaway was investments in developer tooling was always really important. I think Stripe has a pretty good reputation for this, that has always embraced building developer tools. Stripe built, for example, Sorbet, which is a type checker for Ruby, which is roughly similar to TypeScript for JavaScript. So basically built a whole in-house programming language to write higher quality Ruby. But those changes were always good. They gave your engineers more leverage, gave your engineers enhanced productivity. But now what we see is that those investments we made early on in developer productivity are absolutely essential for agents. So if we had not invested in building Sorbet, which is our type checker for Ruby, our agents wouldn't have a type checker to validate their work, which means much more, they perform much worse, and you need more humans in the loop to actually review the code and explain to the agent why it's failing. So those investments we made up front in static analysis, writing our own linters, testing, having like really strong CI infrastructure. Like Stripe has over 5 million tests that we run on every pull request. I think I was talking to someone in CI today. I think we have over 25,000 cores running on every single pull request build. So those investments that we made up front were like, it was great to have fast CI for our engineers, but now that we have tens of thousands times more engineers, and by engineers I don't mean humans, I mean agents, there's many more agents running builds in CI right now at Stripe than there is humans. Those developer tools are like super high leverage things for agents to have, and it boosts like the productivity of the whole org massively. Yeah, that's a very quick introduction to minions and coding agents at Stripe.